analytical techniques, we have observed till now what is the electroanalytical methods, what do you understand by spectroscopic methods. Along with it, we have already seen the UV visible spectroscopy's instrumentation part. So spectroscopy is basically the use of electromagnetic radiation for the identification of the sample. We can use anyone. We can use UV, visible, IR, any other regions also, right? So depending upon the region which is used here, we can further convert our spectroscopy, or we can nomenclaturize our spectroscopy depending upon it. In UV visible spectroscopy, when we deal with it, the range will move from 200 nanometers to 800 nanometers, in which 200 nanometers to 400 nanometers is the range of UV, while 400 to 800 nanometers is the range of visible. So the samples which are transparent or which are colorless in nature are generally observed in UV region, while the samples which are colored in nature are observed in visible range. So here what we can observe, that we can use both the regions to analyze any kind of sample. Generally it has been observed that UV visible spectroscopy is being found in each and every chemical laboratory, in each and every research and development laboratory, and even in higher education departments also. It has been observed that a normal sample of food can also be analyzed through it, while a huge sample of protein can also be analyzed through UV visible region or through UV visible spectroscopy. So it's an instrument which has many advantages, which involves easy instrumentation, easy operation, cost effective, precise results, accurate readings, and even actual identification can be observed through UV ranges. So if we talk about the instrumentation part, so we all know that as with the dispersive IR, the time is required to cover the entire UV visible band due to the mechanism of changing wavelengths. Here we have already seen that we get a monochromatic one, and then we have a splitter, right? So in which we get the particular split of the bands. So one band will be moved towards the sample tube, while another one will be moved towards the reference one. So we need to make sure that we have a changing of chemical bands present here, and when we have changing of chemical bands present, at that time certain kind of fluctuations can be observed. So a recent improvement can be seen using the diode array spectrophotometer. So here a prism, generally a dispersion device, breaks apart the full spectrum which is transmitted through the sample. So we can have two different types of dispersion devices. One is a grating, second one is the prism. So prism gives us a very good result, which is used in diode array spectrophotometers. But generally grating will not give us that much great results, right? So nowadays in advanced instrumentation, we use only and only such kind of prism as a dispersion device only. And each individual band of UV is detected using PMT or using individual diodes. What do you mean by PMT? So PMT stands for photo multiplier tube here, right? Which is a very specific detector for UV visible. So what is the meaning of here, that photo multiplier tube? So we get here an n number of series of anodes present there. So if we get a very poor signal, a single signal is observed, which will further multiply through the diodes, through the multiplication anodes which are present there. Generally the anodes are used here. So from a single signal, it will be moved or multiplied into a number of signals, and our result can be prepared along with it, right? This is the way how it works. Now let's talk about its applications. So if we talk about it, qualitative as well as quantitative, both the types of analysis can be done using UV visible spectroscopy. Widely used for analysis of organic as well as inorganic compounds. It can be used for both of them. It can be used for detection of impurities in the sample, as I said earlier, in food analysis laboratories, in chemical analysis laboratories, even in normal oil analysis laboratories, oil production units, each and everywhere. It is widely used. Okay. It is used for analysis of explosives, widely used for analysis of pharmaceuticals, analysis of water samples. Along with it can be used for analysis of any kind of NDPS substances like narcotic drugs and psychotic substances. It is widely used in forensics for the analysis of any kind of crime scene. Whatever we get from that crime scene, we can analyze it for the analysis of any kind of polymer material to the ranges of small kind of chemical which is observed. We can analyze it through UV visible spectroscopy. So in this manner we can say that it is most widely used one, right? Now let's move ahead to our next technique, which is IR spectroscopy. As the name itself suggests, IR stands for infrared spectroscopy. So IR spectroscopy is concerned with the study of absorption of infrared radiation, which generally causes the vibrational transition in the molecule. The vibrations, okay, different kinds of vibrations are observed like scissoring, rocking, wagging, etc. And when we impart a light on it, they absorb the light and they will move from ground state to excited level and we will measure it, right? So hence, IR spectroscopy is also known as vibrational spectroscopy, right? It has been observed that it is known as absorption spectroscopy or rotational vibrational spectroscopy, because each and every molecule contains rotation and vibrations on their own bonds. Either they will move like this, either they will move in any direction, and at that time it absorbs the light. Okay, it absorbs any kind of radiation. So here the energy of the molecule can be calculated by the formula, which is energy of the molecule is equal to electronic energy plus vibrational energy plus rotational energy. So three phenomena can be easily observed, right? And here we have a range, three different ranges are used in IR spectroscopy. Number 1, near IR. Number 2, mid IR. And number 3, far IR region, right? So near IR region will move from 1 to 10 micrometers. Mid IR region will move from 10 to 100 micrometers, while far IR region will move from 100 to 1000 micrometers. Two different units can be used here for identification purposes. Number 1, micrometer. Number 2, centimeter inverse. These are the regions in which we can identify IR radiation, which can get emitted, which can get absorbed in that particular spectroscope. Now let's move ahead to the principle of IR spectroscopy. If we talk about it, then the molecules are generally made up of atoms which are linked by chemical bonds. And the movement of atoms and the chemical bonds like spring and balls, which are also known as vibrations. This particular characteristic vibrations are called natural frequency of the vibration. Each and every molecule shows this natural frequency of vibration in it, right? So when the energy in the form of infrared radiation is applied, then it causes the vibration between the atoms of the molecules, and when applied infrared frequency matches or is equals to the natural frequency of vibration, then absorption of IR radiation takes place and a peak is observed. Now this particular peak will give rise to the identification of the compound. It can be used for qualitative, it can be used for quantitative purpose both. So different functional groups absorb characteristic frequencies of IR radiation and hence gives the characteristic peak value. And therefore IR spectrum of a chemical substance is fingerprint of a molecule for its identification, right? If we talk about the selection rules for IR spectroscopy, we can say that number one, the elements or the compounds in which dipole moment changes occurs are known as IR active compounds. So only and only the compounds which are IR active in nature gets analyzed in IR spectroscopy. Okay, while the second one is the compounds in which dipole changes does not occur are known as IR inactive compounds. Okay, two different kinds of criteria are there. Number one, IR active. Number two, IR inactive. If we talk about instrumentation, generally lies just as of the UV visible. First is light source. It sends the particular light to the monochromator. Monochromator will send the light to the splitter. There the radiation will move in two directions. First is in sample, second one is reference. Then the particular kind of absorption, vibration frequency will be observed and gets detected through the detector or recorder, right? So here, as we all know that the similar way, the dispersive IR, the lamps illuminate the particular band of IR. The monochromator, generally used is prism, gradually changes the small bands into radiation. Send it to the splitter, goes to the sample and reference tubes and moves ahead to the detector, right? So as with the dispersive IR, the time is required to cover the entire band due to the mechanism of changing wavelength. And nowadays we use prism for it. Okay. So if we talk about the applications, qualitative and quantitative, both the kinds of analysis can be done. Widely used for analysis of organic compounds, not widely used for inorganic ones. Make sure that. Then it is widely used for detection of impurities, used in quality control departments as a quality assurance of pharmaceutical products, used in plastic and rubber industries for quality checking purposes, and used in diatomic molecules in which we can get analyzed H2Cl